Let's discuss one of the most important theorems in statistics, the central limit theorem. Here we're going to try to understand what a sampling distribution of a statistic is, and we have a definition. The sampling distribution of sample means is a distribution obtained by using the means calculated from random samples of a specific size taken from a population. We're going to walk through what this means in an example. We'll also see that some statistics are better than others for estimating population parameters. And that's going to become important to us when we move into inferential statistics in Chapter 7 all the way through Chapter 11. The value of a statistic, for example, the sample mean, depends on the particular values included in the sample, and generally it varies from sample to sample. We call this sampling variability or sampling error. We talked about sampling error last in section 1.3 when we were talking about the different ways we can sample, such as simple random sample, systematic sample, stratified, cluster. And the sampling error is expected. It cannot be prevented. This is something that naturally happens when we take a sample. So let's begin with a simple example. We're going to have a population consisting only of the values 1, 2, and 5. Let's say, for example, we are a company that sells socks, and we can sell those socks as single pairs, 2 pairs, or 5 pairs. We're going to randomly select samples of 2 with replacement. Remember that with replacement means we can select it again. We select a number, we look at it, we put it back, and we have that same probability of taking that again. So we'll randomly select samples of size 2 with replacement, but first we're going to find the mean, the median, the range, the variance, standard deviation, and proportion of odd numbers for this population consisting of those 3 numbers. So we need to find all of these different parameters for our population of 3 numbers. We can use technology or a calculator. I'm going to switch over to technology. Okay, I have my 3 population values, and I have all of the different parameters that I need to calculate. Notice these are parameters, not statistics, because we're talking about a population. So population, we calculate parameters. Our mean, we're going to use that average function, and I'm just going to put all 3 of them in there. 2.67, 2.6 repeating. I can use the median function here. My median is 2, which makes sense. 2 is in the middle. For range, I don't have a built-in function for range, so I can do this one of 2 ways. This is a small size proportion, which is intentional. I want you to be able to understand where these values are coming from this small set of numbers. For the range, I would just take 5 minus 1 and get 4. But if I have a bigger population that I need to find the range for, and I don't want to sort them, maybe it's really big, then I can say maximum of my population minus the minimum of my population. And that will also give me the range. Now remember, my maximum is 5, my minimum is 1, so 5 minus 1 will give me 4. This formula should also give me 4, and it does. For the variance, I'll use VAR for variance. I have a lot of options. I'm going to use .p because I'm working with a population. And so we'll put the variance in there, variance.p, my population values. I get 2.8 repeating. Standard deviation, I would just take the square root of the variance. Let's just use the built-in function for standard deviation. Notice the square root of 2.8 repeating is the exact same value. So keeping in mind the relationship between variance and standard deviation. For the proportion of odd numbers, this is a little bit more difficult to use built-in functions. And without introducing several new functions to you all at once, we're going to use our intuition on this. So come back over here. I have 3 numbers. So proportion, I would take the total, that's my denominator. Odd numbers, how many odd numbers do we have? 1 is odd, 2 is even, 5 is odd. So I have 2 odd numbers out of 3 total. I'm going to calculate that right here. And I'm going to make my technology give me the decimal equivalent. So I'm not going to just type in 2/3. I'm going to type in equals 2 divided by 3. So I get that 0.6 repeating. Okay? So here are all of our different values. The mean 2.7. The median is 2. The range is 4. The variance would be 2.9. Standard deviation would be 1.7, and my proportion 0.7, or I'm going to keep this one as 2/3. I'm not going to round my proportion of odd numbers because the raw numbers that we see here that are not rounded, even though in this representation all of my decimals are rounded, I want you to be able to see when we create the next part of this example just how close or far these numbers are from our next round of calculations. So in my table here, I'll write down my parameter values. These are parameters. My mean is 2.7, median is 2, range is 4, variance is 2.9, standard deviation is 1.7, proportion of odd numbers 2/3, which would round to 0.67. And there we have the parameters of our very, very small 1, 2, 5. Now we're going to take all the possible samples of 2 values from those numbers 1, 2, and 5. How do I know there are 9 of them? Well, if I have a sample of 2 and I have 3 numbers to pick from, I have 3 numbers for the first choice and 3 numbers for the second choice. So I have 9 total different samples. This is going back to that 4.4 section on counting. So if you flip the page, you'll see a table here. I have this table replicated in Excel. I also have this file linked so that if you wanted to use my existing file, you could, instead of recreating your own. So let me switch back over to Excel. I'll make this a little bigger for us. Okay, I have my table here, just like what's in your packet. And this sample of 2 part, I want to put the numbers separate because I'm going to use those built-in functions to calculate things. So I have my sample of 2, 1, 1, 1, 2, 1, 5. Let's go ahead and write the rest of them. So I've used up all of the samples that have 1 as the first item selected. So I'll start with 2. I can have 2, 1, 2, 2, 2, 5. And then for the next group, I can have 5 starting, and then 1, 5, and then 2, 5, and then 5. And yes, we have some samples that will give us the same values, so 1, 2, and 2, 1, but we look at them as different because of the order in which we're sampling them. And we want all of the possible samples we can have to see what's going on. So now let's calculate the mean, average, and I will grab both of them. So I'm using those cell references. Hopefully you've noticed I do this a lot when I use technology. And that's because since I referenced the first 2 numbers, now I can take that handle, hold down my mouse button, and drag it all the way down, and I get all of my means. For the median, I can do the same thing. Median, take my 2 numbers, change the mouse to the plus just by hovering over that square handle. Hold down the mouse button, drag down, and we fill out the next group. My range, I can do the same thing as I did before. Maximum minus minimum. If I do it this way, then I can drag down. But if I try to click on things and subtract, notice my maximum and my minimum change positions in the sample over here. So in this one, my maximum is 2 and 5, but then when I switch to 2 being the first one, 2 is the maximum and 1 is the minimum. So without sorting everything and moving things around, if I just use the max and min functions and reference, I can then drag and I get my range for each one of those samples. Variance, same thing, only this time I have a sample, not a population. These are samples. So I'm going to do var.s, grab the 2 values that I need. Now this one, because my sample values are the same, 1 and 1, my variance and my standard deviation should be 0. And they are. We'll see that in the 3 that have the repeating values, 2, 2, 5, 5. Our variance is 0. Standard deviation, stdev.s, and we'll grab the numbers. And this is just the square root value here, square root of the variance. And then my proportion of odd numbers, this is a little bit harder, so we're just going to calculate by hand. Looking at the first sample, 1, 1, I have 2 odd numbers out of 2 total. The second sample, 1, 2, I have 1 odd number out of 2 total. The third, 1, 5, I have 2 odd numbers out of 2 total. And we're going to see this pattern throughout. 2 and 1, I have 1 out of 2 odd numbers. 2 and 2, I have 0 out of 2 odd numbers. 2, 5, I have 1 out of 2 odd numbers. 5, 1, both are odd, 2 out of 2. 5, 2, 1 out of 2 is odd. And 5, 5, both are odd. For each one of these statistics, we're going to find the mean. So I'm going to find the mean of the mean column. Average. I'm going to start and select all of those 9 different sample means. And I'm going to do the same here for the median, but what makes this great is because I did a cell reference, I can take that and drag it right. Okay, so I'm just taking the mean of each one of these sample statistics. The mean of the mean, the mean of the median, the mean of the variance, the mean of the standard deviation, and the mean of the proportion of odd numbers. And I want you to notice and compare what happens between the mean of the statistics and the population parameters that we calculated before. And now the question is, does the sample statistic, which is in this row, does the sample statistic mean and the population parameter value land on the same value? So here for the means, yes, these are the same 2 numbers, 2.66667. How about for the median here? No, they are not the same. For the range? No. For the variance? Yes. The standard deviation? No. And the proportions? Yes. When we use a sample statistic to estimate a population parameter, some of them are good in the sense that they target the population parameter. The mean, the variance, and the proportion of odd numbers. That proportion could have been the proportion of even numbers instead, but proportions in general. Let's switch back over to our notes. The statistics that we say target the population parameter, that means that when we find this sampling distribution of sample means, the statistics average to be the population parameter, the original population parameters. We call these statistics unbiased estimators. And we have 3 of them. We found that the mean, the variance, and the proportion all are unbiased estimators. So when we go into inferential statistics, starting in Chapter 7, we focus solely on the mean and the proportion in these unbiased estimators. For our class, we don't cover the variance. When we take samples of size n from the population, the mean of the sample means will be the same as the population mean. We just saw that. The mean of my sample means was exactly the same as the population mean. The standard deviation of the sample means will be smaller than the standard deviation of the population. And we see that here, our standard deviation was 1.25 of the sample means, but our standard deviation of the population is 1.7. So we got a smaller standard deviation. The standard deviation is a biased estimator, not targeting that population standard deviation. And it turns out, as we increase our sample size, when we create the sampling distribution, as we increase our sample size n, the shape of the distribution of the sample means will approach a normal distribution. It does not matter what our original population was. And it turns out the mean of the sample means is equivalent to the population mean. And the standard deviation of the sample means is called the standard error of the mean. And we get a new formula, sigma sub x bar is equivalent to the original population sigma divided by square root n. It actually turns out that this formula for this standard deviation will become very important to us momentarily. The sample means approach normality regardless of the shape of the original distribution. So here's an example of moving through sampling distributions from a very strange original distribution. So here we have this really funky, sharp distribution purposefully created. And then when we start taking samples of small size from this original distribution with replacement, we end up with kind of a normal. Not the best one. It starts out kind of normal and then it has this weird leg to it. But then if we take a larger size, notice how quickly, and then a larger size, we're getting that normal distribution shape. This is pretty powerful. It's so powerful that we give it a name. This is called the central limit theorem. As the sample size n increases without limit, the shape of the distribution of sample means taken with replacement from a population with mean mu and standard deviation sigma will approach a normal distribution. That normal distribution will have a mean of mu just like the original population and a standard deviation of sigma divided by square root n. We're going to be using the central limit theorem when we consider a sample of things instead of just an individual thing. So the other 2 sections in Chapter 6, we focused on one item, one person, one teacher. Now we're going to be looking at a group and talking about what's the probability for that group having an average of a value. And because we have a group, our standard deviation is smaller. We have less variability than an individual. And so we will change our standard deviation using this formula, sigma over square root n, and then we'll do the calculations just as before using this new standard deviation.